Hi students, welcome to the session. I am Dr. K. Varada Rajkumar, Associate Professor, Department of CSC, AIML, MLR Institute of Technology, Hyderabad. In our previous class, we discussed about binary search tree. In this session, we will learn about AVL trees. Overview of the presentation. In this presentation, first we see AVL tree definition and how to insert a node in AVL tree. Outcome of this lecture, at the end of this lecture, you all are understand how to insert a new node in AVL tree. AVL tree definition. AVL trees are a type of self-balancing binary search tree. So, AVL tree is also a binary search tree. So, what is the properties of binary search tree? Always the left side node value is less than or equals to root node, and always the right side values greater than or equals to root. That is a binary search tree definition. Now, AVL tree is also a type of self-balancing binary search tree. Here, what is balancing? So, what is balancing? So, balancing means the heights of the left and right subtrees of any node differ by at most 1. So, let us consider this. So, here 10, 6, 16, 2, 8. So, consider this binary search tree. Okay. Now, so what is the height of this leaf node 2? 0. So, what is the height of 8? 0. What is the height of 6? The left subtree height is 1 minus the right subtree height is 1. 1 minus 1 is 0. So, this we call as a balancing factor. Okay. So, similarly for 10, so what is the height of left subtree? 2 minus what is the height of right subtree? 1. So, 2 minus 1 is 1. Yes. For 16, right and left there is no, 16 is the leaf node. So, here the balancing factor is 0. So, now, so coming to definition, here how we find the balancing factor? Heights of the left and right subtree of any node differ by at most 1. So, for example, here in this case, if I insert 1 here, now what happened? The height of left subtree is 3, right subtree is 1, 3 minus 1, 2. Now, it is not AVL tree, but it is a binary search tree. So, this balancing will provide efficient insertion, deletion and searching operation, all with a time complexity of big O of log n, where n is the number of nodes in the tree. Okay. So, consider this example. Now, you check, is this tree is AVL tree or not? Or not. So, how we can check? Start from leaf node, this, and find balancing factor. So, what is the balancing factor for 20 here? So, how we find the balancing factor? So, heights for 20 there is no left and right, so it is 0. For 40, 0. For 30, left is 1, right is 1, 1 minus 1, 0. For 50, left is 2, right is 1, so it is 1. Now, for 70, the left is 3, right is 2. 3 minus 2, 1. So, it is balanced. For 80, it is 0. For 100, it is 0. For 90, left is 1, right is 1, 1 minus 1, 0. So, what is the definition? The heights of the left and right subtrees of any node differ by at most 1. If you observe here, the heights are not differ more than 1. So, it is AVL tree. Now, consider this example here. So, 20 balancing factor is 0, 40 0. So, 30 0. For 50, the left is 2. So right subtree height is 0. 2 minus 0, 2 here. So it is not AVL tree. It is not AVL tree, but it is a binary search tree. It is a binary search tree, but it is not a AVL tree. Okay. So why we need AVL trees? Okay. So for example, so these are the nodes I am given to insert into binary search tree. Okay. 90, 100. Now construct binary search tree. First node 10, 20 is greater, so traverse 20 is right of 10. Now 30, so 30 is greater than 20, so 30 is greater than 20, so 30 is right of 20. 40, so 40 is right of 30, 50 is right of 40, 60 is right of 50, 70 is right of 60, 80 is right of 70, 90 is right of 80, 100 is right of 90. So this is binary search tree. Okay. If you observe here, for example, I want to search for the number 100. Now what is the time complexity here? The time complexity is big O of n. Why? To access the 100, we can traverse all the nodes so present in the tree. If you observe, it seems like linked list. So for 10 there is no left side, and for 10 the 20 is at right side. Now to access 100, we start from 10 and we access all the nodes, so the accessing time will be increased in binary search tree. How we solve this disadvantage we are facing in binary search tree is by using AVL tree. So what is the AVL tree? AVL tree is a self-balancing binary search tree. Now if 10, 20, 30, now so what is the balancing factor here? 0, here 1, here 2. Whenever the balancing factor is more than 1, then we are going to balance the tree. So that is the concept in AVL tree. Okay. So let us see in depth of AVL tree. So let us see what are the common operations we are going to perform on AVL tree. Similarly, binary search tree, here also we perform 3 operations. One is insertion, second one is deletion, so third one is search. Insertion means you are trying to insert new node into tree. So deletion means you are trying to delete a node from the tree. Searching means you are going to search for a particular element present in the tree or not. Okay. So let us see insertion in AVL tree. To insert a new node into AVL tree, start by performing a standard binary search tree insertion. So first, when we try to insert a node in AVL tree, that is same as insertion in binary search tree only. So compare the value. If it is less than the root node, then traverse to left side, otherwise traverse to right side. Okay. Now after insertion, check whether the balancing factor of any node violates the AVL property. So what is the AVL property? Balancing factor K equals to height of left minus height of right. Now if this value differ by more than 1, then we can balance the tree. If the balance factor of a node becomes greater than 1 or less than minus 1, if it is greater than 1 or less than minus 1, so rotations are performed to rebalance the tree. Okay. So we have here the problem is, for example, this is the 10. So what is the balancing factor here? 0 only. after 10 if I insert 20, now 20 is the right child of 10. Now check the balancing factor of 20, 0, balancing factor of 10, 1. So it is also AVL tree. Now I try to insert 30. Now what is the balancing factor of 30? 0. What is the balancing factor of 20? 1. Balancing factor of 10 is 2 now. Okay. So why 2? The left subtree is 0 minus right subtree is 2. Here we consider mod value. 0 minus 2, 2. So it is not a AVL tree. It is not AVL tree. Now we perform, rotations. Okay. Now if you observe here, this is the tree. So how we balance means, if the 20 is root, 10 is left and 30 is right, now it is balanced. By using some rotations, we change this previous tree as like this. So this tree we call as AVL tree. When we try to insert any node in AVL tree, we have two cases. One is the rotation is not required, another case is rotation is required. So consider this AVL tree. Now I try to insert node 75. So what is the algorithm? Insert as like binary search tree. Now compare 75 with 70. Now 75 is greater than 70, so traverse to 90 here. Now compare 75 with 90. 75 is less than 90, so traverse to left side. Now 80, so compare 75 with 80. Yes, 75 is less than 80, so we insert the 75 as a left child of 80. Here the 75 is less than 80, so insert 75 as left of 80. Now this is the insertion, that is the first step. Now what is the second step? Check the balancing factor. Now we start from leaf node. Now 20. So what is the balancing factor of 20? So balancing factor of 20 is the left subtree height and right subtree height. There is no left and right, so here it is 0. For 75, 0. For 30, left is 1, 1 minus right is 0. So 1 minus 0, 1 here. For 60, 0. For 50, 2 minus 1, 1. For 70, this is the 3. Left subtree height is 3, right subtree height is 2. 3 minus 2, 1. For 80, it is 1. For 100, 0. For 90, left subtree is 2, right is 1. 2 minus 1, 1. So if you observe here, it does not violate the AVL tree property. How? Here the balancing factor of all the nodes not more than 1 here. Okay. So here in this case rotation is not required. Now in this tree, if I try to insert node 10, now 30, 20, this is the 10. Now if you observe here, the balancing factor for 30 is 2 minus 0, 2. So it is greater than 1. So we are going to apply some rotations. Okay. Here we apply the rotations based on some conditions. Here we have 4 conditions. Those are left condition, left right condition, right condition, right left condition. So first we see left condition. So now here I try to insert 10. Now you see what happened. So 10 is less than 70, so traverse to left side. So 10 is less than 50, so traverse to left side. 10 is less than 30, so traverse to left side, and 10 is less than 20, so insert this new node as left of 20. Now second step is find the balancing factor. For 10 the balancing factor is 0, for 20 it is 1, for 30 it is 2, so the AVL property is violated. In which condition? If you observe, the condition is left and left, okay, left and left, so the rotation will be right. Okay, so now consider this 30, 20, 10, so left, left. Now we rotate to right side, so rotate to right. Now it becomes 20, 30, 10, that's it. So this is the tree: 70, 50, 20, 30, 10, 60, 90, 80, 100 after rotation. Okay, now consider this tree and insert 25. Now 25 is less than 70, so traverse to left side. So 25 is less than 50, so traverse to left side. So 25 is less than 30, so traverse to left side. 25 is greater than 25, and 20 right is null, so insert 25 as right of 20 here. Okay, what is the second step? Calculate balancing factor. For 25 the balancing factor is 0, for 20 the balancing factor is 1, for 30 the balancing factor is 2. It violates AVL tree property. So next you identify the condition here. What is the condition here? The property is violated in left, right condition. So this is the left and this is the right. So here we apply left right rotation. Okay, consider this 30, 20, 25. Now so once rotate to left side, so now it becomes 30, 25, 20. What is the next rotation? Right. When we rotate to right side, it becomes 25, 30, 20. That's it. So the resultant tree is 70, 50, 90, 25, 20, 30, 60, 80 and 100. Okay, so consider this AVL tree and insert 120. So what is the algorithm? 120 is greater than 70, so traverse to right side. So 120 is greater than 90, so traverse to right side. 120 is greater than 100, so traverse to right side. And 110, so 120 is greater than 110 and 110 right is null, so I insert, so 120 as a right child of 110 here. Insertion is completed. So next step is check the balancing factor. Here 120 balancing factor is 0, 110 balancing factor is 1, so 100 balancing factor is 2 here. How we get the 2? The left subtree height is 0 minus the right subtree height is 2. So 0 minus 2 minus 2, here we take the mod value. So it is 2 here. Okay. So now you identify the condition. What is the condition here? For violating this, the condition is right, 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 right. So the solution is left rotation. So consider this 100, 110, 120, right, right. So the rotation is left. Once we rotate to left side, it becomes 110, 100, 120. That's it. Okay. Now the tree will be changed as 110, 100, 120. Okay. So consider this AVL tree and insert 105. So 105 is greater than 70, 105 is greater than 90, 105 is greater than 100 and 105 is less than 110. So 105 is inserted as left of 110. Now check balancing factor. So what is the balancing factor of 105? 0. For 110, 1. For 100 it is 2. Okay. Now the AVL tree property is violated. How it is true? How it is true? The height of left subtree is 0, right subtree is 2, mod value 0 minus 2, 2 here. So the AVL tree property is violated. Now identify the condition. In which condition it violates? Right, and this is the left. So the rotations is also right rotation, left rotation. Consider 100, 110, 105. Now rotate to right side. If you rotate right side, it becomes as 100, 105, 110. So next rotation is left rotation. Now it becomes as 105, 100, 110. That's it. Now what is the resultant tree? So this is the resultant tree. So 105, 100 and 110. Okay. I hope you all are understand how to insert new node in AVL tree. So coming to summary of this session. In this session we learn about how to insert new node in AVL tree. So in that first we discussed about what is AVL tree. So AVL tree are a type of self-balancing binary search tree. The heights of left and right subtrees of any node differ by at most 1 here. So how we find balancing factor k equals to height of left subtree minus height of right subtree. If the balancing factor of a node becomes greater than 1 or less than minus 1, so rotations are performed to rebalance the tree. So we have 4 conditions. Left condition. If this happened, then rotate to right. If left right condition, then the rotations is also left right. If the condition is right right, then the rotation is left. If the condition is right left, RL condition, then the rotation is also right left. Okay. In next class we see how to delete a node from AVL tree and how to search an element in AVL tree. Thank you.